We're at the dawn of a revolution in neural engineering. It's a new field, one that's built on the idea that we can understand, repair, or enhance our minds. Today, we're talking with Max Hodak, one of the original co-founders of Neuralink. But today, he's the founder of a new company called Science. But what is Science up to?
So we think of ourselves primarily as a neural engineering company, and we've been able to use that to restore vision to patients with very late-stage macular degeneration.
Join us as we get the first ever exclusive look into Science Corporation's HQ, where we learn how they're dramatically reducing the cost of entry for new neurotech startups, about their brand new neural probe, and get a look into the future of what our minds may look like. Imagine a world where blindness can be cured with a tiny implant, where neurological disorders are a thing of the past, and where our brains can seamlessly interface with computers to unlock abilities we've only dreamed of. This isn't a distant future. It's the mission of Science Corporation, combining with fields of neuroscience and biotechnology into a new field known as neural engineering. And in this episode of S3, Science is revealing a brand new device, specifically a probe, what BCI companies use to interact with our brains, except this is a brand new, only ever seen in research kind of probe called a Biohybrid. Let's start by defining what a BCI is. A BCI is a brain-computer interface, and there are three main parts that make one. There's the probe, the part that actually contacts the brain tissue. Then there's the head stage, which connects the probe to the network. And then there's the software that interprets it all, and lets companies like Max's interact with brains.
So this isn't your first rodeo with BCIs, is it?
No, so I started my career back in 2008 working in a lab doing original multi-unit motor decoding in monkeys in a lab at Duke. And then in 2016, ended up co-founding Neuralink with 7 others. And I was president there for about 4.5 years. And then in 2021, co-founded Science. I mean, when I see a person, I think you can really arguably separate it into 2 parts. There's the agent and there's the robot. And biology makes some great robots, but the thing we're really interested in is the agent. And the brain it's the only organ that doesn't make sense in concept to talk about transplanting. You can get a new heart or a new liver. So there's something really special about the brain. In some really profound sense, the brain is you. There's a poster on the wall in the office that says, alter the brain, alter reality. And we think that this is such a powerful substrate for designing important technologies of the future.
For thousands of years, we've peered into the depths of space and plumbed the ocean's darkness. But perhaps our greatest frontier lies within our own minds. Neural engineering isn't just about curing disease or enhancing our abilities. It's about understanding the very essence of human consciousness, the electrical symphony that makes us who we are. And we've barely scratched the surface. We have just 5 senses in which we glory, in which we recognize and celebrate, senses that constitute the sensible world for us. But there are other senses, secret senses, sixth senses, equally vital, but unrecognized and unlauded. These senses, unconscious, automatic, had to be discovered. That quote is from The Man Who Mistook His Wife for a Hat, a legendary book in the field of neuroscience that Max recommended I read. But this is the promise of neural engineering. It's not just about expanding human capability, but it's a journey to finally understand what makes us human.
So we have a lot to talk about in this episode, and new thing that you guys are going to tell us a lot about. But what is the first big kind of vision thing, no pun intended, that you've been working on and has been a focus for Science for the past few years?
When we started the company, we had a thesis that time was right to create a device that would restore vision in some forms of blindness, where the rods and cones had been lost, but the optic nerve was still there. Patients had grown up with vision, lost it in adulthood. This is the vast majority of cases of blindness. And specifically going in through the retina, which was something I hadn't worked on before. Obviously, a lot of prior companies had attempted, but we thought that the technology had now gotten to a place where this would be possible, and that seems to be being borne out. We've worked internally both on optogenetic gene therapies, as well as earlier this year, we acquired a smaller company called Pixium, bringing in really clever stimulation technology that works in just the high resolution central vision area of the eye. The device is called Prima. The way the Prima device works is so the retina covers the back surface of the eye. And then in the front of the eye, you've got the pupil and the cornea, but there's a little gap between where the cornea ends and the retina begins, and you can come into the eye without doing really any damage. And so we make a little hand tool, which is an injector. They first make a couple injections. That eye goes dark and numb for a couple hours. And then they use this inserter to place this little solar panel chip under the retina in the back of the eye, specifically under the macula, the area of the couple center degrees of high resolution color vision. And what it does is where the photoreceptors, the rods and cones, which are the light sensitive cells in the eye, those have died, but the next layer of cells, the bipolar cells, are still there. And so it acts essentially as electronic photoreceptors. And so what you're able to do is bypass this dead layer of cells and get the visual signal kind of back into the optic nerve at the first possible opportunity, which would be the bipolar cells. And then when you hit this with a laser, it activates those remaining bipolar cells and conveys the visual signal into the brain. The Prima device is currently towards the end of a 38-patient pivotal trial in Europe. Got 32 at the 2-year follow-up. Our next step is to write up the marketing approval and submit to the competent authorities in Europe. And we're hoping to have it on market in 2026. Like, if this is all we did as a company, I think it would be a lot to be proud of. Like, I grew up, my mom's dad had retinitis pigmentosa. I grew up around blindness. I have memories of him using a magnifier when I was a kid. And so it is important to remember that this is a big deal. With that said, it is also a big commercial product. I think in the BCI field, there's a lot of promise and potential, and I think many of us are really excited about what feels to be closer and closer. The thing that will determine if that happens or not is if there are some big commercial successes that really enable us and the rest of the field to continue to invest. And when I look around at what BCI products are capable of doing that, a treatment for blindness like this really is up there. That we think this is a multi-billion-dollar a year product in the long run.
If you're a neurotech startup, normally, to build the 3 parts of your BCI, you need a lot of money. But science has already spent this R&D money, and now they're opening up their products for others to benefit from.
I'm one of the co-founders of Science, and my background is in software.
So you're probably the right person to ask this to. What is a BCI?
The 3 parts of a BCI are the probe, the head stage, and then application software. So the probe is the part that actually contacts the brain. The head stage usually convert the signal to digital, and then you can optionally also transform it or try to compress it and then stream it out somewhere. And then application software is what catches it on the other side.
Let's break down what science has developed and how most BCI systems work, in reverse, step by step, starting with the software.
On this monitor here, this is some data that we recorded from one of our subjects. So this is broadband neural data. This, to be clear, is not our visualization software. This is a common program that people use called OpenEphys, but this is recorded through our software stack called Synapse. One kind of problem with neural data collection is that often you can't stream out the full broadband data because it is just a lot of data. And so you often will run things to transform it and compress it on head. And so Synapse makes it easy to write and then bring up these signal chain nodes in like a modular way. You can see that it is a little bit hard to just get meaningful signal out of this. And kind of the steps of cleaning this data are like first put it through a bandpass filter. So here's what that looks like once you've done that. And as you can see, you get this flat signal where you can start to look for these action potentials. And then you can string a spike detector after that to actually look for these spikes. And after that, you can kind of send them out in different data formats, but some common ones are you'll time bin the data and then count spikes. So you can say in this 25 millisecond period, I saw 3 spikes. Or you can send out like, this spike occurred at this exact timestamp. And our signal chain is capable of doing both of these things.
But to get all of that digital interpretation from the electromagnetic frequencies our brains operate on, you need a head stage, a pass-through and a processor between the world of brain and bit. And science built something to do just that they call sci-fi.
So I'm Marit, I'm the lead of the electronics team here at Science. We primarily work on the hardware design, the implant design of all electronics of it. One of the big issues with like the legacy systems, one, they're not built for the current gen of neural devices and the next gen. And they're also really bulky and they're very expensive.
Traditional BCI hardware is quite archaic. It has really kind of delicate and tiny and hard to plug connectors. And you usually stream it off to a cart that has signal processors on it that is huge. It costs $300,000. It is really annoying to wheel around, I can tell you, because I've done it a lot.
So we built this thing here. This is called the Sci-Fi 1. This device, it uses like a USB 3.2 port for connecting to any further probes. And so that gives you about a bandwidth of up to actually 5 gigabit per second. And then we have a Wi-Fi link to stream the data off from Sci-Fi to some kind of laptop or a PC. And we're getting around 850 megabits. And so this is already something like 20 to 30 times better than any other system that's available.
And last but not least, you need a way to capture the electromagnetic signals of the brain in the first place. This is where probes come in. But all of these probes, and pretty much every other probe that other BCI companies use, have a few big limitations. And that is where Science's probe comes into play.
So this is one of our Axon probe implementations. You've got our Axon probe and you've got like a cell well here. What this probe would try and do is you could run experiments where you're putting neuronal cultures onto this sort of MEA, this electrode array. And then you can run some kind of like brain dish-esque experiments where you're trying to see activity from these cultures. And you also even stimulate them using our micro LEDs. So you can run a kind of closed loop BCI experiment using just cells. With any kind of BCI experiment, what you really want to do is to minimize your noise of your recordings as much as possible. And one of the ways you get that is by moving your data sampler as close as possible to the electrodes. And so that's one thing that we've done on this device, but there's this larger chip here on the substrate, and that is our custom designed silicon. And so we put this like right next to the MEAs, and we've been able to reduce the noise all the way down to around 5 microvolts RMS, which is more than sufficient for any kind of neural recording. So here we have like a sort of typical MEA probe experiment setup. You would use one of the Sci-Fi head stages here, and then you would have one of these Axon probes. And so starting from where the probe actually is, it's inside this sort of cell well, this hollow tube. That's where the cell media goes. This then goes a little bit upstream where the analog data is digitized, and then it gets serialized over a standard USB protocol over to the Sci-Fi head stage. And then with its onboard Wi-Fi modem on there, it then streams the data to your device, be it like a laptop, a desktop, or anything, even a phone potentially. So like one of the key strengths of Science is that we have this like heavy vertical integration. We've invested quite heavily in our ability to provide awesome software, hardware, and probes. But this doesn't come cheap, like if anyone wants to start their own BCI company, they would need to essentially go through all of these steps again. The costs are astronomical typically. And so what we're trying to do by releasing these 3 different parts across software, head stages, and probes is that cost to actually spool up a startup doing neurotech goes from being in excess of 100 million to potentially lower than 5. So it just makes it much more accessible.
There's a general concept I learned about while filming this episode that is sort of referred to as there's no space in the brain, meaning that it's so small and so compact with water and neural tissue, there's no place to put anything. And any probe, no matter how small it is, will inevitably kill tens of thousands of neurons. But Science Corporation may have found a solution to this. They are currently building something that's only ever been done in research before, and it's called a biohybrid device.
So what's the limitation with traditional BCI probes, and what if you guys built that might be an answer to that?
So the probes are matched to applications. And so there's many different applications that could use many different types of probes. So this is not that one is going to be strictly better than the other. The stuff that we're doing here is not going to be like the perfect end all be all for every possible BCI application. But there are some that are really uniquely enabled, we think, by extremely high bandwidths in and out of the brain. And with any penetrating electrode, no matter how small or how flexible you think your device is, there's no free space in the brain. The brain is like wet, it's squished together, it's tightly compacted. It's incredibly dense. Every time you put something into the brain, you cause a sterile injury that destroys thousands of cells.
I think most BCIs have a substantially bigger distance between that chip, which is digitizing the actual potentials or stimulating, and the actual electrode, which is doing it. And that means that you have to stick that electrode into the brain to record from a cell, which is already into the brain. In doing so, you destroy everything above it and around it. But you also have a very long, tiny wire that has to send these analog signals that are very small in amplitude from the brain all the way back to the chip for digitization. There's all sorts of potential failure modes that can occur there. So the big difference is that interface going into the brain in our device is made by an engineered cell that we put there. And we know from decades of work that transplant cells into the nervous system, they will grow through the neuropil, they will form synapses, they will receive synapses and integrate into circuits. So we're betting that ours will do the same, even though their cell body is trapped in our device, where we can stimulate and record from it.
So unlike traditional probes that use metal electrodes inserted into the brain, the Science Biohybrid probe is built from an array of specialized chips. Between these chips are tiny spaces known as trenches, where engineered cells are embedded in a hydrogel. Once the device is placed on a subject, these cells grow out of the trenches and into the brain itself, forming organic synaptic connections. This is a completely new paradigm for brain-computer interfaces, unlocking unprecedented opportunities for research and treatment.
So first we need some microenvironment that these cells are happy to grow in. So the first thing we have to do is come up with a microenvironment that cells survive. And that microenvironment also needs to allow us to read and record the state of those cells. We do electrical recording and optical stimulation. So doing electrical recording and optical stim allows us to keep those separate, do stim and record simultaneously at all times. Now we're releasing a preprint with some of the early results that we did in rodents that really convinced us that this was possible. Kind of the initial proof of concept that said, yes, we can get these wired into the brain, we can send information in through them, this is available to behavior. And so that in itself is a pretty cool result. We want to share that with the field. This is, like I said, not totally novel. People have been doing things in this vein for a while, but it does feel pretty neglected. And we would like more of the field to find it exciting and be working on it. There's a huge amount of technology development and biology to do, to say nothing about the neuroscience. And this is much bigger than us. And we want to be part of a much bigger revolution that I think is coming in neurotech. And that requires many more people other than us to be thinking about these things.
In a traditional sense, you would implant a device, and it would probably be a microchip for a high bandwidth application, but you would stick the microchip in and then hope that it connects with the cells already in the brain, and that connection has to happen while the body tries to recover from that surgery. On the other hand, what we do is we take this set of microchips and then we add the cells directly to them, and these are basically cells inside the lab. So the cells grow onto the chip, form a nice robust interface, and then we transplant the entire thing on top of the surface of the brain and allow the cells to grow in and form a cell-to-cell connection.
Another reason the Biohybrid probe is such a big deal is that it allows for a much higher channel count compared to traditional 2D chip-based electrode systems, which are limited by the physical constraints of channel wiring. This allows for much improved targeting of individual neurons and synapses, instead of only relying on electrical stimulation, which has a much wider area of effect.
So it starts with the chips. These chips we design in-house, then are fabricated TSMC. They come back as dies from a wafer. We take those dies, we turn them back into like pseudo wafers. Once that is done, we put electrodes for recording chips or micro LEDs on them for stimulation chips. And then we also put copper pillars on the chips as well. Then we take those chips, put a spacer on top of them to create a space for the cells to live in. And then we actually bond the chips together, face to face or back to back, in a repeating pattern for how many of our chips that we want. And at that point, it goes to receiving cells.
They start off as stem cells. By the time they get into our devices, they're fate-committed neurons or neural progenitors that can only give rise to neurons and glia. And we have some fixtures where we can force them in there. They stick to the sides, they start proliferating, they fill up the trench. We cap them with a hydrogel, which allows them to get some support, keep growing. But the hydrogel, it forms holes that are big enough for axons and dendrites to go through, but not for cell bodies, really. And sort of the whole thing is encased in this package. And then that package sometimes will be leaving culture for months to get those neurons to really mature. We have a number of molecular cell biology assays that we use to look at whether the neurons are active, whether they form synapses, whether they express the right things that would indicate that they're the right cells. We can also transplant those guys into mouse models, principally. Still early days for this type of work, but this is really pointing the way that allows us to access many regions of the brain distally, and we can get at them more naturalistically by activating basically a presynaptic neuron and having the signaling be via chemical synapses rather than zapping it with a large electric field, which will activate everything in a cubic millimeter.
So basically, in order to fit a million channels of interconnections, a planar chip is not sufficient. So instead what we do is we make a number of planar chips and then we stack them together on top of each other, and that creates a 3D volume of chips. And that allows us, in the smallest possible footprint, to get as many transistors as possible. And that allows us to connect with the number of cells that we need.
So we do a number of CRISPR and other types of genome edits to do a couple of things with them. We put in a switch, basically, where we can give it a small molecule that will accelerate its maturation into a neuron. We put in the gene that renders it sensitive to light once it becomes a mature neuron, where we can stimulate an LED. We do several CRISPR edits to hide it from the immune system. And this is something that increases the ability of the cell to engraft into the brain. It gives us the potential to place where they're off the shelf. We can use the same cell for any recipient. And we also put in a edit that allows us to kill those cells with a safe small molecule, which is already FDA approved in case anything goes wrong or in case someone doesn't want it anymore, take a pill and they shall die. This is an example of one of our implants in mice. You can see sort of these cell boluses here, the cells that were in the trenches. So in this implant, the trench has been removed for processing. The cyan dots here are nuclei, so the nuclei of the mouse. And then anything that's yellow is human cells, so it's a protein only in humans.
The basic bet of biohybrid devices is that going to significantly higher channel counts, if you can even really think of it in terms of a channel count. I mean, here, conventionally, you think of your channels as your number of electrodes. Here, we've got number of cells, which is a little bit different than number of electrodes. And more importantly, the number of synapses that you get. Like if we load a biohybrid device with 1 million cells, it is possible you could get up to 1 billion synapses in the brain. And so we're really at the early stages of figuring out how to informationally use these types of devices. But in the near term, we think of them as communication BCIs, the extension of the motor BCIs that are being developed today. The brain communicates with the world. It does this through language, it does it through muscles, and we hope that these will be able to be communication devices that allow us to think in terms of potentially kilobits or even megabits of bandwidth instead of bits per second. In the long run, it's possible that these devices could be used for some really novel stuff, but we're at I'd say the early stages of beginning to flesh that out.
So with all the work that you've done in your life with neuroscience, how has this sort of changed, or has it changed, like how you think about being human or consciousness?
I mean, I've always had a personal interest in understanding what is consciousness? What does it mean to perceive things? Where does all of this come from? And it's clearly rooted in at least no small part in these computations happening in the brain. That is so slippery. It's like very famously, many generations of smart people, like as soon as you feel like you have an interesting idea, it slips through your fingers. And to be clear, we're not there, but I'm optimistic that more progress will be able to be made in the next decade than people think. And I think that the path there runs through tools and technologies like this.
So why does all of this matter? Why should we be excited about this? Science Corporation and other BCI companies aren't just developing a new technology. They're developing a platform that could redefine how we interact with our own biology. This isn't only about curing diseases and restoring lost functions. It's about enhancing the human experience at its core.